Look up at the cosmic web on a dark night and you are looking at the largest known structure in the universe. Thin filaments of hydrogen plasma, tens of millions of light years across, threading the cosmos in a vast lacy framework, with galaxies strung along the filaments like beads on a wire. The mainstream story says that structure is held together by gravity, the gravitational pull of dark matter forming the scaffolding, ordinary matter falling into the gravitational wells, the geometry emerging from the initial density fluctuations of the early universe. That story is, in broad strokes, almost certainly right. But there is a second possibility, taken seriously by a minority of plasma physicists and dismissed by most of the rest of the discipline, that the filaments are also threaded with vast electrical currents so large the numbers become hard to hold in mind, and that a force law derived 200 years ago at a workbench in Paris, then quietly removed from the textbooks a century later, might be coupling distant parts of those currents in a way the standard simulations do not include. What if the cosmic web is not just structure but conversation? Settle in. Subscribe so you can join the next journey and stick around, because the question we're about to follow connects a candlelit Paris laboratory in 1820 to the largest structure in the universe tonight. Let's begin. Part 1. The compass that twitched. It is the spring of 1820 in Copenhagen, and a Danish physicist named Hans Christian Ørsted is standing in front of his students, with a wire, a compass and a battery, and he's about to break a wall that has stood for more than 2,000 years. The wire runs across a wooden table, the compass sits a few inches away. The battery is what they called in those days a voltaic pile. Alternating discs of copper and zinc separated by cardboard soaked in salt water, the first device in human history capable of producing a steady, controllable electric current. Ørsted is in the middle of a lecture on the relationship between electricity and heat. He has been doing this for years. He has done this exact demonstration before, and then this time, when he closes the circuit and the current begins to flow through the wire, the needle of the compass moves. It moves only a little. The deflection is small enough that the students might not have noticed it if Ørsted had not pointed at it. The needle does not swing toward the wire the way you would expect if the wire had somehow become magnetic. It does not swing away from the wire either. Instead, it rotates so that it lies perpendicular to the wire, at a right angle to it. When Ørsted reverses the direction of the current in the wire, the needle rotates the other way, still perpendicular, still at a right angle. The geometry is rotational. The geometry is not what any known force does. I want you to feel the weight of what just happened in that room, because if you do not feel it, the rest of this story will sound like a footnote. For more than 2,000 years, electricity and magnetism had been treated as two completely unrelated mysteries of the natural world. The ancient Greeks knew about both. They knew that amber, when rubbed with a cloth, would attract small bits of dust and feathers. They had a word for amber, electron, and that word would become, eventually, our word for electricity. They also knew about lodestones, naturally magnetized chunks of iron or mined from a region in Asia Minor called magnesia, and the word magnesia would become, eventually, our word for magnetism. Two phenomena, two unrelated curiosities. Amber pulled dust, lodestones pulled iron. They did not seem to talk to each other. For 23 centuries, no serious investigator suggested they were the same thing. Newton, in the late 1600s, treated magnetism as one of the unsolved problems of natural philosophy and considered electricity barely worth investigating at all. Benjamin Franklin, in the 1750s, flew a kite into a thunderstorm and proved that lightning was the same kind of stuff as the static electricity you could rub off a cat, but he did not connect it to magnetism. Coulomb, in the 1780s, formulated the law of force between two stationary electric charges, and separately, a similar law for the force between two magnetic poles, and the similarity between the two laws was noticed and admired and then set aside. The walls between the two fields were intact when the 18th century turned into the 19th. They were intact when the voltaic pile was invented in the year 1800. They were intact in 19 of the 20 centuries since the Greeks had named both phenomena, and then, in a small lecture room in Copenhagen, a compass twitched. Ørsted was not, by 19th century standards, a famous scientist. He was a competent professor at a small Scandinavian university. The kind of physicist whose work would have been remembered, if remembered at all, as a series of solid contributions to a respectable career. He had been working on the relationship between electricity and chemistry, electricity and heat, electricity and most other things, for about 10 years. He had a philosophical commitment, inherited partly from German romantic natural philosophy, to the idea that the apparently separate forces of nature were probably aspects of a single underlying unity. But he had not been able to demonstrate it. He suspected electricity might be connected to magnetism. He had set up demonstrations to try to find the connection. He had failed. He had been failing for about 10 years. The reason he failed before the spring of 1820 is illuminating. He had been looking for an electric current to produce a force on a compass needle in the same direction as the current. He had set up wires parallel to compass needles, expecting the needles to swing along the wires the way iron filings will line up along the length of a bar magnet. The needles did not swing. He concluded the effect was either not there or too small to measure, and moved on to other experiments. What happened in the spring of 1820 was that he set up the wire perpendicular to the compass needle, not parallel, and this time, when the current flowed, the needle moved. The deflection was perpendicular to the current, not parallel. The geometry was rotational. He had been looking for an effect that obeyed the wrong symmetry. When he stopped looking for it and saw what was actually there, the effect had been waiting for him the whole time. There is a lesson in that, and the lesson will return more than once in this video. The physics of the universe is not always shaped the way the most reasonable initial guess says it should be. Sometimes the law you're looking for is not the law you're going to find. Sometimes, when you finally see what is actually there, it will be sideways from what you expected, and you will understand in the same moment why no one before you had noticed. Ørsted spent the next 3 months running controlled trials. He varied the strength of the current. He varied the distance between the wire and the needle. He moved the wire to the other side of the needle and watched the deflection reverse. He tried different metals for the wire. He tried different shapes for the wire. The effect was robust. It was reproducible. It was small, but it was real. By the middle of July, he was ready to publish. The publication was a 4-page pamphlet, written in Latin so that it could be read across Europe, titled Experimenta circa effectum conflictus electrici inacum magneticum, which translates to experiments on the effect of an electric conflict on the magnetic needle. The phrase electric conflict is Ørsted's own. He was groping for vocabulary that did not yet exist, and his guess at what to call the thing the wire was doing did not stick. The deflection of the needle did stick. The pamphlet appeared on the 21st of July 1820. Within a few weeks it had been reprinted in French, in German, in English. By early September, a copy had reached Paris. The man who brought it was named François Arago, and Arago was an astronomer and a politician, and a member of the Académie des Sciences, and he was also, importantly, a personal friend of a 45-year-old French mathematician named André-Marie Ampère. On the 4th of September, 1820, at the regular Monday meeting of the Académie at the Institut de France in Paris, Arago stood in front of his colleagues. Pierre-Simon Laplace was there, Joseph-Louis Gay-Lussac was there, Augustin Jean Fresnel was there. The whole roster of the most powerful scientific minds in continental Europe was in the room, and he set up Ørsted's apparatus and reproduced the demonstration. The wire, the battery, the compass. The needle twitched. The room went, as the historical accounts have it, very quiet. Ampère was in the room. He had heard of Ørsted's pamphlet but had not yet seen the experiment performed. He watched the needle move, and he understood, in the way that occasionally happens to a mind already prepared by years of relevant thought, that what he was watching was not a curiosity. It was the first sentence of a science that did not yet exist. I want you to picture him as he leaves the institute that evening. He is 45 years old. He has had a hard life. His father was guillotined during the Terror in 1793 when he was 18, and the experience left him with a melancholy that never fully lifted. He has spent most of his career working on mathematical analysis, on probability theory, on the foundations of calculus. He has done good work, but not great work. He has never had an idea that anyone outside a small circle of French mathematicians would remember. He's walking home through the streets of Paris in the early autumn dusk, and he has just realised that the rest of his life is going to be spent on one problem, and that the problem is going to be the largest problem he will ever encounter. He goes home, he does not sleep, he starts building. Part 2. The 7-day cycle. What Ampère does over the next 7 days has very few parallels in the history of science. The closest analogues, Newton's 18 months at his mother's farm in 1665 and 1666 during the plague, Einstein's miraculous year of 1905, are stretches of months, not days. Ampère gives himself a week, because the Académie meets again on the 11th of September, and he intends to have something to say. He commandeers his own apartment as a laboratory. He sends a servant out to buy wire, copper wire, in lengths long enough to bend into curves and coils. He builds frames out of whatever wood is at hand. He suspends the wires from silk thread so they can swing freely. He sets up his own voltaic pile, an instrument that, in 1820, you could not simply walk into a shop and purchase. He assembles the discs of copper and zinc himself, soaks the cardboard separators in brine, stacks them, and waits to see whether they produce a current. He does not bother to write down what he is doing in this first week. We know what he did because he reproduced the demonstrations publicly 6 days later, and because his correspondence in the following months describes the apparatus in detail. He starts with the question that Oersted's pamphlet did not quite ask. Oersted had shown that a current-carrying wire exerts a force on a compass needle, that is, on a magnet. Ampère asks, what if you replace the magnet with another current-carrying wire? What does a current do to another current? He sets up 2 wires parallel to each other, suspended on silk, free to swing. He passes a current through both of them in the same direction. The wires move toward each other. They attract. He reverses the current in one of them, so that the 2 currents are now flowing in opposite directions. The wires move apart. They repel. I want you to stop and sit with this for a moment, because the answer Ampère is getting is the exact opposite of what stationary charges do. 2 stationary charges of the same sign, 2 positive charges, or 2 negative charges, repel each other. This is Coulomb's law, established a generation earlier. It is one of the most reliable rules in physics. 2 stationary positives push each other apart. So if you take 2 wires and pump positive current through both of them in the same direction, your most reasonable initial guess is that they should repel, because the moving positive charges should still push on each other the way stationary positive charges do. They do not repel, they attract. This is the first place in our story where the universe deviates from what intuition says it should do, and the deviation is not subtle. It is, in the strictest sense, backwards. 2 parallel streams of positive charges flowing in the same direction pull toward each other. 2 parallel streams of positive charges flowing in opposite directions push apart. Stationary charges with the same sign always repel. Moving charges with the same sign sometimes attract. The motion changes the rule. Ampère runs the experiment. He runs it again. He varies the current. He varies the distance between the wires. He confirms in less than 3 days the basic geometric pattern. Same direction, attract. Opposite direction, repel. He's 45 years old and he's alone in his apartment, and he's taking the first steps into a country that no one has mapped. Then he starts crossing the wires. He suspends one wire so that it lies perpendicular to a second wire, the 2 of them like a plus sign in mid-air. He runs a current through both. The wires twist. There is a torque between them. The perpendicular wire wants to rotate so that it lies parallel to the second one, with both currents flowing in the same direction. Ampere measures the torque. He varies the angles. He confirms a pattern. The force between two current-carrying wires depends not only on the distance between them, but also on the angle between them, and on the angle each of them makes with the line connecting them. There is geometry inside the force, and the geometry is rich. By the third or fourth day, he has moved on to coils. He takes a long copper wire and winds it around a wooden cylinder, turn after turn into a tight helix. He removes the cylinder and runs current through the wire. The coil, now suspended on silk threads, behaves like a bar magnet. It has a north end and a south end. It is attracted to iron. It repels other coils of the same orientation. It attracts coils of opposite orientation. He has built, with copper wire and a battery, something indistinguishable from a magnet. This is the move that changes everything. Magnetism, for 2,000 years, had been a property of certain rocks and certain pieces of iron, treated as a mysterious force of nature with no obvious source. Ampere has just demonstrated that you can manufacture it from copper wire and current. He proposes, and this is the proposal that will eventually be vindicated by atomic physics 100 years later, that all magnetism is in fact made of currents. The magnetism in a lodestone is not a separate fundamental force. It is the collective effect of countless microscopic loops of current circulating inside the iron. Magnets are not magnetic. They are electric. There is no separate magnetic charge. There are only currents. The wall between electricity and magnetism is not just broken. It is dissolved. He coins a word for the coil, taking it from the Greek for tube, solenoid. The word will outlive him by 2 centuries. Every electric motor you have ever heard of, every speaker in every set of headphones, every relay in every car, every magnet in every hospital MRI machine, is a solenoid in the Ampere sense, a coil of wire carrying a current, behaving as a magnet because of the currents inside it. He sees all of this in his apartment in the first week. On the 11th of September, 1820, exactly 1 week after Arago's demonstration, Ampere walks back to the Institut de France carrying his apparatus. He stands in front of the same room. He sets up the 2 parallel wires. He runs the current. They attract. He reverses one. They repel. He shows the crossed wires twisting. He sets up the solenoid. He explains, in the voice of a man who has not slept properly in 7 days, that magnets are made of currents, and that the science of electricity and the science of magnetism are about to become one science. He does not have a name for the unified science yet, but within a year he will give it one: electrodynamics. The room is, again, very quiet. Laplace is not given to dramatic statements, but he writes about Ampere in the weeks that follow with a respect bordering on awe. Gay-Lussac understands immediately what has happened. Fresnel, the architect of the wave theory of light, sees implications for his own work that no one else will articulate for 40 years. Ampere continues reporting to the Académie weekly through the autumn of 1820. By the end of the year, he has built the first crude galvanometer, an instrument for measuring current that uses, as its sensing element, the very deflection of a compass needle that Ørsted had discovered in Copenhagen. He has formulated the earliest version of what is now called Ampere's circuital law, the equation that relates the magnetic field around a current to the current itself. And he has proposed, as a working hypothesis, a quantitative force law between 2 infinitesimal segments of current, a law that the rest of his life will be spent refining. 7 days. The science of electromagnetism, the science that will run every electric grid on the planet and every chip in every device you own, was begun by one man, alone in his apartment, in 7 days. The pattern of it, the first formulation of it, the first solenoid, the first galvanometer, the first hypothesis about the force law, all of it, from the 4th of September to the 11th of September, 1820. I want you to remember the 7 days. We're going to come back to them at the end of this video, and when we do, you will understand why I am asking you to remember them now. Part 3. The Knife Edge Balance. The first week was the beginning, but it was not the science. The science came over the next 6 years, and the work of those 6 years was done largely in silence, with very few witnesses, in laboratories that no longer exist, on apparatus that no longer survives, by a man who was, by all accounts, increasingly absorbed in a problem that his colleagues admired but did not always understand. To follow what Ampère did between 1820 and 1826, we have to follow him into the lab, and we have to look at the instruments he built, because the instruments are how he got the law. The law was not, in the end, a flash of insight in a Paris apartment. The law was a measurement. What he needed was a way to measure the force between two very small segments of current, not between two long wires, which gives you a useful but blurry average. He needed to know what one tiny piece of current does to another tiny piece of current, at every angle, at every distance, in every geometric configuration he could construct. Because he believed, and the belief turned out to be correct, that all electromagnetic phenomena would be explicable as the sum of these tiny segment-on-segment interactions. If he could figure out the law for one pair of segments, he could build any current configuration he wanted out of segments, and predict the forces between them. It was an atomistic approach to electrodynamics, and it was, in its time, a radical idea. The problem was that the force between two short segments of current is very small, so small that to measure it, he needed an instrument capable of detecting fractions of a milligram of force on a wire just a few centimeters long. The instrument he built for this is called a knife-edge balance, and a version of it sits today in the Musée des Arts et Métiers in Paris, restored and behind glass, but mostly silent about the years it spent in active use. The knife-edge balance works like this. Picture a wooden frame about the size of a small bookshelf standing on a stone bench in a Paris laboratory in 1822. From a crossbar at the top of the frame, a horizontal beam is suspended on a single steel knife edge, a wedge that allows the beam to rotate freely around its center point with almost no friction. At one end of the beam, a short segment of copper wire is attached, formed into the shape Ampère wants to test, a straight piece, or a circular arc, or a small coil. At the other end of the beam, a small counterweight balances it. The whole assembly is so delicate that a breath of air will set it swinging. Below the suspended segment fixed to the frame is a second segment and the test object. Ampère connects both segments to a voltic pile through carefully arranged wires that bring current to them from a distance. In a geometry he has designed so that the currents in the connecting wires do not contribute to the force he is measuring. He closes the circuit. Current begins to flow through both segments. The suspended segment moves. He measures how far it moves by reading the rotation of a small mirror attached to the beam. A lamp at the other end of the room throws a spot of light onto the mirror, and the mirror reflects it onto a graduated scale on the opposite wall. The smallest force on the suspended segment produces a measurable swing in the spot of light. The scale is graduated finely enough that he can resolve forces down to a few thousandths of a gram on a wire only a couple of centimeters long. This is precision work in a room where the only light is daylight from the window and a single oil lamp on the wall. The voltic pile has to be replenished with fresh brine every few hours. The wire connections corrode and have to be cleaned with sandpaper. The silk threads stretch and have to be retied. Ampère does this himself, sometimes with a single assistant, often alone. He records the measurements in notebooks that survive today, written in a tight, hurried French with corrections in the margins, sometimes with the date noted at the top of a page, often not. The measurements are organized by geometric configuration, first the parallel case, then the anti-parallel case, then the perpendicular case, then a series of arbitrary angles. Imagine him at this bench in the early 1820s, the Paris laboratory, the late hour, the candle burning down beside the notebook. The brass of the knife-edge balance catches the lamplight as the beam rotates. Two short wires hanging on silk threads from the wooden frame, currents released through them by the voltaic pile in the next room. The balance tips by a measurable amount in one direction, when the currents run side by side, parallel and same sense. It tips by a measurable amount in the opposite direction when the currents are aligned head to tail along the same line. Ampere records both numbers. The first of those numbers will be taught in physics classrooms for the next 2 centuries. The second of those numbers will not. Right now, in the late hour at the bench with the candle burning down and the spot of light tracing across the wall, the 2 numbers look equally real to him, because they are equally real. He spends 6 years on this work, not full-time. He has teaching duties at the École Polytechnique, he has family responsibilities, he has correspondence to maintain with the rest of the European scientific community, who write to him constantly about the new science he has begun. But the experimental program is continuous, and the precision improves year by year. By the middle of 1824, he has measured the force between current segments in every geometric configuration he can think of. He has explored what happens when the segments are short, what happens when they are long, what happens when they are at every angle to each other, what happens when one is curved. And he has noticed something. The force depends on 3 things: the magnitudes of the 2 currents, the distance between the 2 segments, and an angular factor that depends on the orientations of the segments relative to the line connecting them. The angular factor has 2 parts. One part is largest when the segments are side by side and parallel. The other part is largest when the segments are aligned head to tail along the same line. In the side-by-side configuration, the angular factor produces an attraction between the segments. This is the magnetism we are all taught. In the head-to-tail configuration, the angular factor produces a repulsion between the segments along the direction of current flow. This is the longitudinal Ampere force, and this is the part of the law that the rest of physics will eventually decide to forget. I want you to feel the weight of where we are. Ampere is sitting at a bench in Paris with a pen and a notebook and a knife-edge balance, and he has just become the first person in the history of the world to measure, directly, both halves of the force that holds the universe of electricity and magnetism together. One half is the force we will eventually call magnetism. The other half is a force that, 2 centuries later, the discipline he is founding will not have a name for. He measures both. He writes both down. He treats them with equal seriousness because the law that produces them is one law, and the law is the law. The geometry of the world is the geometry of the world, and you do not get to keep the parts of it you like and throw away the parts you find inconvenient. In 1826, 6 years after the 7 Days, he publishes the memoir. The title is Theory of Electrodynamic Phenomena, uniquely deduced from experience, and the title is not boastful in 19th century French scientific style. It is descriptive. He believes, and the manuscript is structured to demonstrate, that every equation in the memoir has been deduced from a measurement, and every measurement has been made on apparatus he can describe in enough detail that a reader in another laboratory can reproduce it. The memoir runs to about 200 pages. It is dense, careful, mathematically demanding. It includes the force law in its full form, a central force, directed along the line connecting the 2 segments, satisfying Newton's third law in the strongest possible sense. Every force equal, opposite and aligned along the straight line between the 2 interacting elements. Newton himself, Ampere is at pains to point out, would have been satisfied. The memoir is received as the founding document of a new science. Within a year, every serious physicist in Europe has read it, or is reading it, or is asking for a copy. The book sells out. The Académie publishes a second printing. Ampere's name becomes attached to the science he has founded. Within his lifetime, the unit of electric current will be named after him, and it still is. The ampere, the amp, the unit you see on the side of every fuse box in every home. He dies in 1836, 10 years after the memoir is published, at the age of 61. He's buried in Montmartre Cemetery in Paris, and the inscription on his tomb is one short line, in Latin: Tandem Felix, at last, happy. The 7 days were the beginning. The next 6 years were the science. The rest of his life had been, the inscription suggests, a long wait to find a problem worth giving himself to. He had found it. He had given himself to it. He had finished it. He had not finished it. None of them know it yet, but the part of his law that the textbooks are going to forget is going to spend the next 2 centuries waiting quietly for someone to come back and look at it again. Part 4. The door inside the equation. I am not going to write the equation on a chalkboard, because there is no chalkboard, but I do want to walk you through what is inside it, in plain language, because the inside of the equation is where the rest of the story lives. If you can hold the shape of the law in your mind for the next few minutes, the displacement of the law from the textbooks 2 generations later is going to make a kind of structural sense that it does not otherwise have. Picture 2 short pieces of wire, each carrying a current. Call them segment 1 and segment 2. Each segment has a length and a direction. The direction is the direction the current is flowing along the segment. Now imagine the straight line drawn from the middle of segment 1 to the middle of segment 2. That line is the line of action. It is the line along which Ampère insists, on the basis of Newton's third law, the force between the 2 segments must lie. The force depends on 3 things. The first thing is the product of the 2 currents. A stronger current in either segment produces a stronger force, in direct proportion. The second thing is the inverse square of the distance between the segments. Just like Newton's gravity, just like Coulomb's law for stationary charges. Move the segments twice as far apart, and the force drops by a factor of 4. This part of the law looks familiar to anyone who has studied physics. The third thing is where Ampère's law leaves familiar territory and goes somewhere the modern textbook formulation does not follow. The third thing is an angular factor, a number that depends on 3 angles. The angle that segment 1 makes with the line of action, the angle that segment 2 makes with the line of action, and the angle between the 2 segments themselves. Now, when you turn the geometric crank on this angular factor, you find that the answer it produces depends sensitively on how you arrange the 2 segments. There are 2 geometric configurations that matter most. Configuration 1. The 2 segments are side by side, parallel, with their currents flowing in the same direction. Think of 2 short pieces of wire running parallel to each other, like railroad tracks, with current flowing along both of them in the same direction. In this configuration, the line of action between the segments is perpendicular to both currents. The angular factor produces a force that pulls the segments toward each other. They attract. This is the magnetism we are all taught. This is the reason that the parallel wires Ampère hung on silk threads in his apartment in the first week of September 1820 pulled toward each other. This is the reason that the 2 coils of the bar magnet demonstration he showed at the Académie attracted each other. This is the reason a transformer works, the reason a motor turns, the reason an MRI machine has the magnetic field it has. The sideways attraction between parallel currents is the workhorse of every electromagnetic device on the planet. Configuration 2. The 2 segments are aligned head to tail along the same line, with their currents flowing in the same direction. Think of 2 short pieces of wire arranged like train cars, nose to tail along the same track, with current flowing along both of them in the same direction. In this configuration, the line of action between the segments is parallel to both currents. It runs along the same line the currents are flowing on. The angular factor now produces something different. It produces a force that pushes the segments apart along the line of action. They repel each other along the direction of their own motion. This is the longitudinal Ampère force. This is the part of the law that the rest of this video is about. Take a moment to feel how strange it is. 2 short pieces of wire carrying current in the same direction, lined up nose to tail along the same line, push each other apart along the direction the current is flowing. The same currents that, in the side-by-side configuration, pull together, in the head-to-tail configuration push apart. The geometry of the law has flipped the sign of the force depending on how the segments are arranged. And here is the crucial detail. These 2 forces, the sideways attraction and the head-to-tail repulsion are not two separate forces. They are not two different fundamental interactions. They are two faces of one law. The single angular factor in Ampere's equation produces both behaviours automatically, depending on the geometry. The sideways attraction is just what the law does when the segments are arranged sideways. The head-to-tail repulsion is just what the law does when the segments are arranged head-to-tail. There is no separate equation for one and a separate equation for the other. There is one equation, and the geometry of how you arrange the segments tells the equation which face to show you. Two faces of one law. I am asking you to remember that phrase, because we are going to come back to it, and when we do, the meaning of it will have shifted. Now. When you take any real circuit, a piece of wire bent into a loop, a coil wound around a core, a transmission line carrying a signal from one continent to another, the circuit is made of an enormous number of these tiny current segments, arranged in every possible orientation relative to every other tiny current segment. The total force between two circuits is the sum of all the segment-on-segment interactions. In any closed circuit, the longitudinal contributions, summed all the way around the loop, integrate to zero, because for every segment pointing in one direction, somewhere else around the loop there is another segment pointing in the opposite direction, and the longitudinal pieces cancel each other out as you go around the full circuit. This is the mathematical fact that the rest of this video hinges on. For closed circuits, that is for almost every electromagnetic experiment ever performed in a working laboratory, the total force you measure is identical to what you would get if the longitudinal piece of Ampere's law did not exist at all. The sideways magnetic part summed all the way around the loops gives you the entire force. The longitudinal part summed all the way around vanishes. So the question of whether the longitudinal force is real is, in most experimental settings, empirically indistinguishable from the question of whether it is not real. You get the same final answer either way. Almost. There is a category of experimental setting where this convenient cancellation breaks down. It is the setting in which the circuit itself is changing, being formed or being broken or fragmenting under stress, fast enough that the closed-loop approximation no longer holds. In those settings, the longitudinal pieces do not integrate to zero. They do real, measurable work, and the question of whether the longitudinal force is real becomes, in those settings, an empirical question with a measurable answer. The exploding wire experiments that Peter Grenoble will run at MIT in the 1980s live in this category. We're going to get to them. But you needed to know, first, what is inside the equation, because the equation is the thing the discipline is going to forget. One law, two faces. One face survived into every modern physics textbook. The other face fell out quietly between about 1860 and 1920 in a process that no one announced and that no working physicist today was alive to witness. We're about to walk into that process. Part 5. Weber carries it across the continent. Before we get to the displacement, I have to tell you about Wilhelm Weber, because if we skip Weber, the displacement looks like a smaller move than it actually was. Weber was a German physicist born in 1804, working at the University of Göttingen in the 1840s, and he is the man who took Ampere's force law and extended it beyond Ampere's wildest hopes. Weber asked the question that Ampere had not quite asked. Ampere's law described the force between two segments of current, pieces of wire with current flowing through them. But what was a current really? By the 1840s, physicists were beginning to suspect, though they could not yet prove it, that an electric current was nothing more than the motion of individual electric charges through a conductor. The charges were the fundamental thing. The current was just charges in motion. If that was right, then Ampere's law, which was written in terms of current segments, must really be a law about individual moving charges. There should be a more fundamental form of the law, written in terms of charges and their velocities, that reduced to Ampere's law when you integrated it over a current-carrying wire. Weber wrote that more fundamental form. He published it in 1846, in the first of what would become 7 major memoirs on electrodynamics, in a paper titled Elektrodynamische Massbestimmungen, Electrodynamic Measurements. The Weber force law gives the force between 2 individual moving point charges, and it includes terms that no force law before it had included. The force depends on the distance between the 2 charges, the way Coulomb's law and Newton's gravity do. But it also depends on the relative velocity of the 2 charges, how fast they're moving with respect to each other, and it also depends on the relative acceleration, how fast that relative motion is changing. This was a radical step. No fundamental force law in physics before Weber had included a velocity dependence or an acceleration dependence. Forces, in the Newtonian picture, were supposed to depend only on positions. Weber's law broke that pattern. He argued that the broken pattern was necessary because the electromagnetic interaction between moving charges genuinely depends on their states of motion, and any force law that pretends otherwise will not match the experimental record. When you integrate the Weber force law over a closed current loop, it reduces exactly to Ampere's force law. When the charges are at rest, it reduces to Coulomb's law. It is, in this sense, a generalization that contains both of the previous laws as special cases. It is also, in another sense, a law that has things to say that neither of the previous laws had to say. It predicts effects between individual moving charges that Ampere's law could not address, because Ampere's law was about currents, not charges. For 2 generations, from 1846 through about 1890, the Weber force law was the standard formulation of electrodynamics across continental Europe. Every German physicist who studied electromagnetism studied Weber. Most French physicists did too. The Italians did, the Russians did, the Dutch did. Across the European continent, the Ampere-Weber framework, currents from Ampere, charges from Weber, was the way you talked about electromagnetism, and the longitudinal force was just one of the predictions the framework made. Weber went further. In 1856, he and Rudolf Kohlrausch performed a measurement that, in retrospect, should have rocked the discipline. They measured the constant that appears in the Weber force law, a constant whose value in 19th century units was hard to predict from first principles. They measured it carefully, using a beautiful experiment that compared the electrostatic and electromagnetic effects of a known charge in a known motion. And the number they got was numerically equal to the speed of light. Let me say that again, because this is one of the great forgotten moments in the history of physics. In 1856, almost a decade before James Clerk Maxwell would derive the electromagnetic theory of light from his own equations, Wilhelm Weber and Rudolf Kohlrausch measured a constant inside the most general available formulation of electrodynamics, and the constant turned out to be the speed of light. They had found the connection between electromagnetism and light empirically, by measurement, before anyone had derived it theoretically. Weber wrote about it. He understood what it meant. He said, in print, that the appearance of the speed of light inside the electromagnetic force law was a strong hint that light itself must be some kind of electromagnetic phenomenon. And then the discipline, for reasons we'll get to in the next part, did not follow the hint. Maxwell did, but he derived it from a different starting point, and the credit and the history went to Maxwell. The Weber-Kohlrausch measurement of 1856 is one of those moments where you can see, in retrospect, that the discipline had the answer in its hands and chose to pick it up from a different angle. The Ampere-Weber tradition was complete enough to predict the constant. The Maxwell-Faraday tradition was simpler to write down. The textbooks went with the simpler one. The older tradition, with its richer set of predictions and its messier mathematics, was set aside. I want you to feel the weight of the alternative history we are looking at. There was a coherent, complete, experimentally tested formulation of electrodynamics that included the longitudinal Ampere force, generalized to individual moving charges by Weber, and that had derived the speed of light empirically from its own force law in 1856. It was taught across continental Europe. It was extended by mathematicians like Carl Neumann and Hermann von Helmholtz. It was treated by the working physicists of the 1850s and 60s as the obvious framework to build on. By 1920, it was no longer in any standard physics textbook. It had not been refuted, it had not been disproven, it had been displaced. We were about to walk into the displacement. I want you to remember, as we do, that the thing being displaced was not a small thing. It was the whole continental European tradition of 19th century electrodynamics. It was a complete, internally consistent, experimentally tested formulation that included the longitudinal force as a fundamental prediction. It was set aside in favour of a simpler, more elegant alternative that did not include the longitudinal force at all. The reasons it was set aside were partly about mathematics, and partly about teaching, and partly about which side of a national border the leading physicist of the next generation lived on. The reasons it was set aside were not in the end about whether the longitudinal force was real. Part 6. The Quiet Displacement. James Clerk. Maxwell is the architect of the displacement, and the displacement is not, in any simple sense, his fault. Maxwell did not wake up one morning and decide to remove Ampere's law from the textbooks. He did not denounce the older formulation. He did not even fail to praise it. He praised it. He devoted an entire chapter of his life's masterwork to it. He called it, in the exact wording that has been preserved in every reprint of his treatise on electricity and magnetism for the last 150 years, one of the most brilliant achievements in science. He understood it. He admired it. He treated it as a finished accomplishment in the history of physics, and then he replaced it. The replacement was a project that took Maxwell about 12 years and was built up across 3 major publications. The first was a paper called On Physical Lines of Force, published in 1861, in which Maxwell tried to build a mechanical model of the electromagnetic field, actual rotating vortices in an actual mechanical ether, all whirring away in space, with electric and magnetic effects falling out as consequences of the mechanics. The mechanical model was, even at the time, recognized as a kind of scaffolding. Maxwell did not literally believe the ether was made of rotating vortices. He used the model because it gave him a way to derive the equations he was hunting for, and the equations turned out to be more important than the model that produced them. The second publication was a dynamical theory of the electromagnetic field, in 1865, in which Maxwell stripped away the mechanical scaffolding and wrote down the equations directly. The equations described 2 fields, the electric and the magnetic, defined at every point in space, and they described how the fields changed in time, propagated through space, and exerted forces on charges. The equations were beautiful. They were also, importantly, written in a mathematical language, what we would now call vector calculus, that was new and powerful and that the discipline was about to fall in love with. The third publication was a treatise on electricity and magnetism, in 1873, in which Maxwell gathered everything he had done in a 2-volume textbook that became, almost instantly, the standard reference for the next generation of physicists. The treatise is the book that did the displacement, not because Maxwell wanted to displace anything, but because every working physicist in the world who wanted to learn electromagnetism in the 1870s and 1880s learned it from the treatise, and the treatise was a field theoretic book. The treatise has, in Volume 2, an entire chapter on Ampere's original force law. The chapter is paragraphs 528 through 531. It runs to about 15 pages. Maxwell explains Ampere's law in full. He praises it. The exact words appear in paragraph 528. He calls Ampere's research one of the most brilliant achievements in science. He notes, and this is the crucial passage, the one that has been quoted by every defender of the original Ampere framework for the last 150 years, that Ampere's law is the unique formulation of the force between 2 current elements that satisfies Newton's third law in the strongest possible sense. Every force equal, opposite, and aligned along the line between the 2 elements. No other formulation, Maxwell says, has this property. And then Maxwell says, in the next breath, that his own formulation, the one in terms of fields filling space, does not satisfy Newton's third law in this strong form. It satisfies it only in a weaker form for closed circuits. For individual current elements, the field-based formulation predicts forces that are not aligned along the line between the elements. The field-based formulation is, Maxwell admits, less elegant in this specific way than Ampere's original law, but it is more compact. It is easier to compute with. It generalizes more cleanly to time-varying fields, to electromagnetic waves, to the radiation that Maxwell will soon predict, and that Hertz will detect in his Berlin laboratory in 1887. The field-based formulation, despite its violation of strong Newton, is the formulation the next century of physics will be built on. Maxwell makes this argument explicitly. He does not call for the displacement of Ampere's law. He simply explains that his own formulation is mathematically more convenient, and that the price of that convenience is the loss of strong Newton at the level of current elements, and that this price seems to him worth paying. The discipline pays the price. By 1880, the Maxwell formulation has become the standard reference across Britain and is spreading to the continent. By 1890, it is the dominant framework in the leading physics journals. By 1900, it is the formulation being taught in every major physics curriculum from London to Berlin to Boston. The last step in the displacement comes with Hendrik Lorentz, the great Dutch theoretical physicist in the 1890s. Lorentz takes Maxwell's field equations, which describe how fields behave but say nothing directly about how individual charges respond to those fields, and he writes down the missing piece. The force on a point charge moving through given electric and magnetic fields, Lorentz says, is given by a compact formula. The charge times the sum of the electric field plus the velocity of the charge crossed with the magnetic field. F equals Q times E plus V cross B. The Lorentz force law. The Lorentz force law completes the field picture in a way nothing before it had completed it. Charges no longer interact directly. They interact only with the field that fills the space around them. The field carries the interaction at the speed of light, no faster. There is no instantaneous action at a distance, because all influence propagates through the field at finite speed. And this is the structural fact that matters most for our story. The force law contains no term that could produce a force on a charge along the direction of its own motion. The cross product, V cross B, is, by mathematical definition, perpendicular to V. The magnetic force on a moving charge is always perpendicular to the charge's velocity. There is no possibility within this formulation of a force along the line of motion. There is no possibility of a longitudinal Ampere force. The framework forbids it, at the level of the equations themselves. I want you to sit with what just happened. The displacement was not a conspiracy. It was not a deliberate erasure. It was a sequence of 3 carefully argued, mathematically motivated, professionally responsible moves by some of the greatest physicists who have ever lived. Maxwell built the field formulation because the field formulation generalized more cleanly and computed more easily. Lorentz wrote down the force law because someone had to write down the force law, and the field formulation needed one. The discipline adopted both because the new framework was more powerful and more compact than the old one. Every step in the process was reasonable. Every step in the process was published. Every step in the process was peer-reviewed by the standards of its day. And the net result was that, between about 1860 and about 1920, a fully derived, experimentally tested formulation of electrodynamics, Ampere's original law, generalized by Weber, used as the standard framework across continental Europe, was displaced from the physics curriculum, and the part of it that the new framework could not accommodate was dropped without any formal retirement, any public refutation, any explicit acknowledgement that something was being left behind. The displacement was not announced because nobody felt the need to announce it. The new framework was simply better at the jobs the discipline was asking of it, and the old framework was simply, gradually, used less often, until eventually it was not used at all. By 1920, No standard physics textbook in the world taught Ampere's original force law. The form of the law that survived was a derived special case, a corollary of Maxwell's equations, applicable to closed circuits, with the longitudinal piece dropped, because in closed circuits the longitudinal piece integrates to zero and is empirically invisible. The Weber framework, which had been mainstream across the continent for 2 generations, was effectively forgotten by the rising generation. New physicists were trained in the Maxwell-Lorentz framework from the beginning of their education. They learned that the magnetic force on a moving charge is Q times V cross B, and they learned that this force is always perpendicular to velocity, and they were not told that there had ever been a competing formulation with different predictions. A 200-year-old, experimentally tested formulation, praised in print by the author of its replacement, fell out of the physics curriculum across 2 generations without ever being formally retired. No one announced it. No one had to. The new framework was easier to teach and easier to compute with, so the old framework drifted out of the textbooks the way a street drifts off a city map when no buses run on it. By 1920, no standard physics curriculum still taught Ampere's original force law. Generations of physicists were trained without ever encountering it. They were not lied to, they were not told. The weight of what happened is in the difference between those 2 things. The discipline did not refute the older formulation. The discipline forgot it, deliberately, the way a city forgets a street that no buses run on. The forgetting was nobody's fault and everybody's responsibility, and it took 2 generations, and at the end of the 2 generations, the question of whether the longitudinal force was real had been quietly removed from the list of questions the discipline was prepared to ask. And there things sat, for 60 years, until, in the basement of a laboratory at MIT in the late 1970s, a research scientist with an unusual education and an unusual temperament decided to take the question off the back shelf and ask it again. Part 7. The Wires That Should Not Fragment. Peter Granot came to the question of Ampere's longitudinal force by a route nobody could have planned. He was born in Berlin in 1921, fled to England as a teenager when the Nazis came to power, served in the Royal Air Force during the war, and trained as an electrical engineer in the post-war years. He did not start out as a foundational physicist. He started out as a working engineer, specializing in the design of high-power electrical equipment, rail guns, capacitor banks, the kind of hardware where currents are not measured in milliamperes but in kiloamperes, and where what the equations say will happen has to match what the metal actually does, or somebody loses an eye. In 1971, he joined the Francis Bitter National Magnet Laboratory at the Massachusetts Institute of Technology, and there he was given access to capacitor banks capable of dumping enormous amounts of energy through small pieces of conductor in microseconds. The Francis Bitter Lab was, at the time, one of the few places in the world where you could routinely run experiments at the kind of current levels where, if Ampere's longitudinal force was real at any scale, you should be able to see its effects directly on the metal. What drew Granot to the longitudinal force question, by his own account, was a problem that had been sitting unexplained in the high-current engineering literature for almost 20 years. In 1964, researchers at the Naval Surface Warfare Center in Maryland had been studying what happens when you discharge a capacitor bank through a thin, straight copper wire. The expected behavior, predicted by standard Maxwell-Lorentz electrodynamics, was straightforward. The current produces a magnetic field around the wire. The magnetic field, interacting with the current itself, produces a radial pinching force. The wire squeezes itself from the outside in, like a sausage being constricted. At the same time, the current heats the wire through ordinary resistive dissipation. If the current is high enough, the heating vaporizes the wire. You get a column of hot copper plasma where the wire used to be. This is well understood. It is what the equations say should happen, and it is mostly what does happen. But sometimes, the naval researchers found, something else happened. At certain combinations of current and pulse duration, the wire did not vaporize. It fragmented. It broke apart into many short pieces each piece a few millimeters long, separated by clean breaks. The pieces fell to the bottom of the experimental chamber as discrete solid fragments. They were not melted. Metallurgical analysis under a microscope confirmed that the break surfaces showed no signs of melting at all. The wire had parted in the solid state. This is a strange result. Standard electrodynamics, with all the corrections you would normally apply, does not have a clean way to produce solid-state fragmentation of a copper wire under a current pulse. The radial pinch force squeezes. It does not break the wire along its length. Resistive heating melts. It does not produce clean breaks at room temperature metal. There were some hand-waving explanations in the literature. Thermal stress from rapid heating, magneto-hydrodynamic instabilities in the molten zone, some kind of Coulomb stress from transient charge imbalances during the pulse. But none of them, by the late 1970s, had been worked out in enough detail to match the observed fragmentation patterns quantitatively. Grano started thinking about the problem in the late 70s. He had read Ampere's original memoir, or rather, he had read about it, since the full English translation would not be available for another 40 years. He knew about the longitudinal force, and he had a hypothesis. If the longitudinal force was real, then a current flowing along a wire was, at every point along the wire, pushing the head-to-tail aligned current segments apart along the wire's length. In a closed circuit, the pushes would cancel, but in a wire short enough, or under conditions extreme enough that the metal could not redistribute the stress fast enough, the longitudinal forces should be able to do measurable mechanical work. They should, in principle, be able to pull a wire apart along its length. He started running experiments. He set up capacitor banks in the Francis Bitter lab, connected them to short copper and aluminum wires, and measured what happened when the pulse was discharged. He varied the wire length, the wire diameter, the pulse duration, the peak current. He photographed the wires before and after, weighed the fragments, measured the lengths of the fragments, looked at the break surfaces under microscopes. He was careful. He was systematic. He was, by training, a working engineer, and engineers know that if your hypothesis is wrong, the metal will tell you, and if your hypothesis is right, the metal will tell you that too. What the metal told him, over the course of several years, was that the fragmentation patterns matched Ampere's longitudinal force law better than they matched any standard electrodynamics calculation he could perform. The force pulling the wire apart along its length, as inferred from the fragment positions and the breaking strength of the copper, was, in his analysis, an order of magnitude larger than what the pinch forces and the thermal stresses combined could account for. The direction of the force was longitudinal, not radial. The magnitude, as a function of current and wire geometry, scaled the way Ampere's force law said it should scale. In March of 1984, he published the first major paper on the subject in the Journal of Applied Physics. The title is a question, Longitudinal Magnet Forces, with a question mark, because in 1984 you could not yet publish in a mainstream physics journal a paper titled Longitudinal Magnet Forces without a question mark. The question mark was the price of admission. The paper appeared in Volume 55, Issue 6, pages 2598 through 2600. It was 3 pages long. It described the experiments. It described the analysis. It concluded that the wire fragmentation observed in his lab and in the earlier Naval Surface Warfare Center experiments was best explained by the longitudinal component of Ampere's original force law, and that the longitudinal force in question had no counterpart in standard Maxwell-Lorentz electrodynamics. The paper passed peer review. It was accepted. It was published. The Journal of Applied Physics is a mainstream physics journal, indexed in every standard database, read by every working physicist in the relevant subfields. The paper was not relegated to an obscure venue. It was not a preprint that never made it through review. It was a real, peer-reviewed, mainstream published paper claiming experimental evidence for a force that, according to the standard textbook framework, did not exist. The response from the physics community was instructive. The paper was not ignored, but it was not embraced either. It provoked, almost immediately, a series of critical responses in the same journal and in others. Papers arguing that the wire fragmentation could be explained within the standard Maxwell-Lorentz framework if you carefully included the thermal stresses, the magneto-hydrodynamic effects, the Coulomb stresses from transient charge imbalances, and several other contributions that the standard back-of-the-envelope calculation usually leaves out. The critics did not, for the most part, deny the experimental observations. They denied the interpretation. They said, yes, the wires fragment. No, you do not need a longitudinal force to explain it. The critics, however, did not in general show their own calculations all the way through. The full energy balance, with all corrections included, was rarely closed in print. The argument tended to be that, in principle, the standard framework should be able to handle the observation, and that the burden of proof was on Granot to demonstrate that no possible combination of standard effects could produce the fragmentation pattern. Granot, for his part, replied that no possible combination of standard effects had ever produced the fragmentation pattern in a published calculation either, and that the longitudinal force interpretation was the only explanation that had been worked out quantitatively and matched the data. This kind of argument tends not to resolve. The two sides talk past each other. The mainstream side says the alternative interpretation is unnecessary because in principle, the standard framework can handle the data. The minority side says the alternative interpretation is necessary because in practice, the standard framework has not handled the data. Both sides are, in some sense, right. The question of whether the longitudinal force is real, in the sense of needing to be added to the standard framework as a separate term, is empirically distinguishable from the question of whether the longitudinal force is merely a convenient summary of effects that the standard framework could handle if it tried hard enough. But making the empirical distinction requires settling the energy balance to a precision that nobody, on either side, has fully achieved in print. So the question sat. It still sits. The Granot papers were not retracted. They were not refuted. They were debated and then, slowly, set aside by the mainstream of the discipline in much the same way that Ampere's original law itself was set aside a century earlier, not because the question had been answered, but because the people asking the question had stopped getting heard. Across the 1980s, Granot and his son Neil, also a physicist, also at MIT for part of his career, published roughly 20 more papers on the subject. The papers appeared in the Journal of Applied Physics, in Physics Letters A, in the IEE Transactions on Plasma Science, in Foundations of Physics. They extended the experimental program. They tested the longitudinal force in new configurations. They published interpretive papers reviewing the cumulative evidence. They wrote 3 books together over the course of 2 decades: Ampere-Neumann Electrodynamics of Metals in 1985, Newtonian Electrodynamics in 1996, and In the Grip of the Distant Universe, The Science of Inertia in 2006. The forgotten formulation was not a historical curiosity. It was a live empirical question that had been on the desk of the discipline for 40 years. The desk was, however, not the desk of the textbooks. The textbooks did not change. New generations of physicists continued to be trained in the Maxwell-Lorentz framework, with no exposure to the Ampere-Weber alternative, and with no awareness that there was an unresolved experimental literature about the limits of the framework they were learning. The question stayed in the literature, but the literature was visited by fewer and fewer people. There is a kind of physicist who is at peace with that situation, and a kind who is not. Granot was not. He kept writing. He kept measuring. He kept submitting papers. He kept attending the small foundations of physics workshops, where the foundational questions still get a hearing, and he kept making the same argument. The wires fragment. The foil throws water into the air. The longitudinal Ampere force is the simplest explanation that has been quantitatively worked out, and the discipline owes it a serious look rather than a polite shrug. He was not, by all accounts, an embittered man. He was a stubborn one. He believed the question was answerable. He believed someone would eventually answer it. He did not, in his lifetime, see anyone answer it. I think it is worth pausing on the human shape of what Grenot spent his life on, because the human shape is not the shape that gets written into journal articles. He was a working engineer who, in middle age, became interested in a foundational question that the mainstream of physics had set aside. He spent the next several decades trying to put the question back on the table. He published the papers, he wrote the books, he trained students, he did the work. The work was acknowledged by the small community that engaged with it as serious and careful. The work was set aside by the larger community of mainstream physics as not requiring immediate attention. He died at 93 with the question still open and his particular contribution to it still mostly unread by the discipline he was trying to address. This pattern, the careful peer-reviewed work, the small community of engaged readers, the polite distance from the mainstream, the unresolved question persisting across decades, is, in my experience, one of the most common shapes that real intellectual standoffs take in modern science. The question does not get refuted. The question does not get embraced. The question gets kept alive by a small group of people who care about it, and the rest of the discipline moves on. Sometimes, eventually, a new generation comes along and looks at the old papers and decides the old papers had something. Sometimes the new generation never comes. The question, in either case, persists. It is one of the realities of how a field as large and slow-moving as modern physics actually advances or fails to advance. Peter Grenot died in 2014. He was 93 years old. He had spent the second half of his life on a question that the discipline could not quite ignore and could not quite embrace, and at the end of his life, the question was no closer to being settled than it had been when he started. His son Neil continued some of the work for several more years. The wires, meanwhile, keep fragmenting. Every time anyone runs the experiment in the right regime, the fragmentation pattern shows up. The standard explanations remain incomplete. The longitudinal force interpretation remains plausible. The discipline remains divided in a way that does not show up in the textbooks, because the textbooks were finalized long before anyone published the question that the wires keep asking. Part 8. The Fountain of Aluminum Foil. Of all the experiments the Grenots designed across their 40 years on the longitudinal force question, the one that has the most visceral hold on the imagination is the aluminum foil fountain experiment. It is the experiment that, if you saw it performed in front of you, would be the hardest to walk away from. Let me take you to the bench. The room is on the second floor of an unremarkable laboratory building on the MIT campus. It is the late 1980s. The walls are painted institutional cream. The floor is tile. The lighting is fluorescent. Overhead fixtures with the slight buzz that fluorescent lighting always has. A capacitor bank the size of a filing cabinet sits against the back wall. It is bolted to the floor because when it discharges, the recoil is not trivial. The terminals of the capacitor bank are connected through thick copper bus bars to a glass tank that sits on a bench in the centre of the room. The tank is about the size of a small fish aquarium. It is full of water, ordinary tap water, no additives, no electrolyte. Suspended vertically in the water is a strip of aluminum foil, maybe 2 inches wide and 10 inches long. The foil is connected at the top and the bottom to the bus bars. The current path goes from the capacitor bank, through the upper bus bar, down through the aluminum foil submerged in water, out through the lower bus bar and back to the capacitor bank. The Grenots, or one of their graduate students, charge the capacitor bank. The voltage climbs. You can hear it climbing. There is a meter on the side of the bank and a soft clicking as the charge accumulates. The student steps back. The countdown is silent. 3, 2, 1. The trigger fires. The discharge is over in milliseconds. There is a bright flash of white light along the length of the aluminum foil. So bright that, even in the fluorescent overhead light, the flash dominates the room for an instant. There is a sharp click, audible across the room, and then, in the same instant, the water in the tank leaps upward, in a column from the top of the foil, in a spray that reaches the ceiling of the room and falls back to the floor, and the bench in a slow patter of droplets that last for several seconds after the flash itself has died. The column of water is unmistakable. It is not a small effect. The water has been thrown into the air with considerable kinetic energy. The Granots measure the kinetic energy by catching the falling water in a graduated container, by photographing the column at high speed and computing the velocity from the frame-to-frame displacement, by measuring the impact on a force-sensitive plate held above the tank. They get consistent numbers. They write the numbers down. The kinetic energy of the water column, in their measurements, is significantly larger than what the resistive heating of the current pulse, deposited in the water adjacent to the foil, could produce by ordinary thermal expansion and steam formation. Stand at the edge of the bench. You can feel the air move when the discharge fires. You can feel the temperature of the room rise by a fraction of a degree from the energy dumped into the water. You can hear the patter of the water falling back. The countdown was silent. The flash was instantaneous. The column lifted into the air with the slow inevitability of something pushed from below by a force that is not announcing itself. The water fell, the foil glowed and faded, and Peter Grano picked up his clipboard and wrote down a number that did not match what the textbook framework predicted the resistive heating should have done. He wrote it down anyway. He wrote it down many times, over many trials, over many years. The number kept not matching. The Granots' interpretation, published across a series of papers in the late 1980s and early 90s, was that the excess kinetic energy in the water column came from longitudinal ampere forces accelerating the water along the foil's length. The argument went like this. The current flowing down through the foil produces at every point along the foil head-to-tail current segments. The longitudinal force pushes these segments apart along the foil. In the body of the foil, the force is balanced by the mechanical stiffness of the metal and by the closed-circuit cancellation when integrated all the way around the circuit. But at the edges of the foil, at the top where the foil meets the bus bar, and at the bottom similarly, the geometry is such that the longitudinal force is partially uncompensated. It pushes the water adjacent to the foil edges, accelerating it along the direction of current flow. The water is pushed upward at the top edge and downward at the bottom edge, and the upward push is what you see as the column leaping into the air. The mainstream response was, again, that the energy balance could in principle be closed within the Maxwell-Lorentz framework if you carefully included all the contributions, the radial pinch forces driving water radially outward from the foil and then upward by hydraulic redirection at the top, the thermal expansion of the heated water adjacent to the foil, producing rapid steam formation and consequent water motion, the magneto-hydrodynamic instabilities at the foil-water interface during the pulse, and several other effects. The argument was that in principle, all of these effects together should be able to account for the observed kinetic energy. The argument was rarely worked out in print all the way through. The argument was that it could be, in principle. The published Grano calculations, by contrast, did the full energy balance using the longitudinal ampere force as the dominant excess term, and got a match with the measurements within experimental error. The Grano calculations could be wrong. They make assumptions about the spatial distribution of the longitudinal force inside the foil, about the coupling of the force to the surrounding water, about the boundary conditions at the foil edges, that are not derivable from first principles in any framework and have to be modelled. But the Grano calculations exist, in print, in peer-reviewed journals. The mainstream alternative, claiming that the standard framework can handle the observation if you include all the corrections, does not exist in print as a fully worked calculation. The discipline has, in this specific empirical case, the rare situation of one detailed calculation predicting the data and one hand-waved counter-argument insisting that a different calculation, if anyone ever performed it, would also predict the data. This is the kind of empirical standoff that, if it occurred in a more visible field of physics, would be the subject of a major experimental program by now. There would be groups at multiple universities trying to replicate the experiment with better instrumentation. There would be theoretical workshops trying to pin down the predicted energy balance in the standard framework. There would be careful comparisons between the two interpretations across a range of experimental parameters. Instead, the experiment lives in a quiet corner of the literature, replicated occasionally by small groups, debated occasionally in foundations of physics workshops, but not pursued at the scale that the question, on its own merits, would seem to deserve. A 200-year-old question has been dressed in modern apparatus, and the discipline still cannot tell you which interpretation is right. The aluminum foil keeps lifting the water. The number on the clipboard keeps not matching. The literature keeps containing two readings of the same column of water, both of which have been on the table since the late 1980s, neither of which has been definitively eliminated. The mainstream framework remains the default, because the mainstream framework remains the default. The longitudinal force interpretation remains a minority reading, because the people advancing it have not been able to make the discipline reorient around them. This is what unresolved empirical questions look like in the wild. They do not get resolved on a schedule. They sit. They wait. They wait sometimes for a generation of physicists who are not trained inside the assumption that the question is already settled. The question of whether the longitudinal force is real is, in the spring of 2026, exactly where it was in the spring of 1990. It is the same question. The same fountains keep leaping into the air. The same number keeps appearing on the clipboard. The same two readings are still on the table. I do not, just to be clear, want to overstate the certainty of the Granot interpretation. The argument that the standard framework could in principle handle the observation is not trivial. There are real corrections, thermal stresses, magneto-hydrodynamic instabilities, transient charge imbalances that have not been fully calculated and that, in some combination, might turn out to account for the excess kinetic energy without requiring any longitudinal ampere force at all. The mainstream view that the longitudinal force interpretation is unnecessary is not, by any stretch, an unreasonable view. It is the view that requires less new physics, and the principle of parsimony has weight in any scientific debate. If the question is ever fully resolved in favour of the mainstream, it will be because someone did the energy balance calculation in full, with all corrections included, and the calculation closed without needing the longitudinal term. That calculation is, in principle, doable. It has not yet in print been done. Until it is done, the question remains, in the strictest empirical sense, open. I am dwelling on this caveat because I want the channel's intellectual honesty to be clear. The longitudinal force interpretation is plausible. It is not proven. The exploding wire fragmentation and the foil fountain energy balance are anomalies, observations that the standard framework has not yet quantitatively accounted for in published form. But anomalies are not refutations. The history of physics is full of anomalies that turned out, in the end, to have prosaic explanations that the standard framework was perfectly capable of producing, once someone took the time to work out the calculation. The longitudinal force might turn out to be one of those, or it might turn out to be a real separate term that the standard framework genuinely needs. The evidence is currently consistent with both readings. The choice between them is a research program that has not, on the mainstream side, been carried out in full. That is the truth of where the question sits. Part 9. Assis carries the memoirs back. If you wanted to read Ampere's original memoir in English, in any year before 2015 you could not. There was no English translation. There were excerpts in some history of physics textbooks, translated by various editors over the years. There were summaries in survey articles that paraphrased the law and described the experiments. But the actual 200-page document, Theory of Electrodynamic Phenomena, uniquely deduced from experience, published in 1826 in the Journal of the Académie des Sciences, in the original French of a 19th-century French mathematician, was not available as a complete English text. Anyone who wanted to read it and who did not read 19th century French could not. This may sound like a small problem. It is not a small problem. It means that for almost 2 centuries, every English-speaking physicist who wanted to know what Ampère actually said about his own law had to either learn 19th century French or trust whatever paraphrase the editor of their nearest History of Physics textbook had decided to provide. The paraphrases varied. Some of them were accurate, some of them were less accurate. None of them included the experimental details that Ampère had written into the memoir as the justification for his law. None of them included the explicit argument for why Ampère had chosen the form of the law he had chosen, an argument that depended on Newton's third law in its strong form, that depended on the precision of his knife-edge balance measurements, that depended on 6 years of experimental work, and that, in the original document, takes up substantial portions of the 200 pages. What this meant, in practice, was that the standard textbook treatment of Ampère's law in English language physics curricula was based not on Ampère's actual argument, but on a derivative summary of his argument, filtered through Maxwell's chapter in the treatise, filtered through Lorentz's reformulation, filtered through whatever paraphrase the textbook author had assembled. The longitudinal force component, in particular, was the easiest piece to drop in this filtering process, because it did not survive the integration over closed circuits, and so did not appear in any practical engineering calculation. By the time the chain of filters had finished, what English-speaking physicists knew about Ampère's law was a derivative of a derivative of a derivative, and the original argument had been effectively inaccessible for 2 centuries. André Koch Torres Assis is a Brazilian physicist, born in 1962, who teaches at the State University of Campinas in São Paulo. He came to electrodynamics through a circuitous route, graduate work in cosmology, a long detour through plasma physics, a personal interest in foundational questions about inertia and Mach's principle. He read the secondary literature on Ampère's law in the 1980s and noticed that the secondary literature was working from translations of translations of translations, and that the original document had never been put into English. He set himself the task of doing it. The project took him, in total, more than 30 years. He did not work on it full time. He did the translation in stretches, between his teaching duties and his other research projects, often with collaborators, Brazilian, Argentinian, American, German, who helped with specific sections or with the historical commentary that he ended up wrapping around the translation. The book finally appeared in 2015, published by a small academic press in Montreal called Apparatus, in a 473-page volume titled Ampère's Electrodynamics, Analysis of the Meaning and Evolution of Ampère's Force Between Current Elements, together with a complete translation of his masterpiece, Theory of Electrodynamic Phenomena, Uniquely Deduced from Experience. The co-translator was J.P.M.C. Chaib, a Brazilian historian of science. The book is a strange object. It is, in one sense, a piece of scholarly archaeology, a careful textual recovery of a document that had been effectively buried in 19th century French for almost 200 years. It is, in another sense, a serious work of contemporary physics, a complete presentation of an alternative formulation of electrodynamics, with all the experimental justifications, all the mathematical derivations, and a C's own commentary on how the formulation compares to the standard textbook treatment. It is, in a third sense, a polemic, an argument that the discipline has been working from an incomplete picture of electromagnetism for 2 centuries, and that the time has come to look at the original picture again. The book has not had the reception one might have expected. It has been bought mainly by historians of science, by a small community of physicists interested in foundational questions, and by the Grano tradition researchers who've been working on the longitudinal force question for decades. It has not been adopted as a textbook in any major physics curriculum. It has not been reviewed in the major physics journals. It has been received by the mainstream of the discipline with a kind of polite acknowledgement that the translation work is valuable for historical purposes, and that the physics contained in the translation is not something the discipline currently has reason to engage with. Assis did not stop with Ampère. Across the years between 2007 and 2021, he produced the first complete English translation of Wilhelm Weber's main works on electrodynamics, the 7 major memoirs Weber published between 1846 and 1878, including the founding paper that introduced the Weber force law for individual moving charges, the 1856 measurement of the speed of light constant with Kohlrausch, and Weber's late papers on the electrodynamic theory of light. The Weber translation runs to 4 volumes. It is, like the Ampere translation, available in English for the first time, and it is, like the Ampere translation, being received by the mainstream of the discipline as a historical curiosity rather than as homework. I want you to sit with what Assis has done, because the work itself is one of the more remarkable acts of intellectual recovery in the history of physics. A single Brazilian physicist over more than 30 years of evenings and weekends has put back into circulation the founding documents of a 2-century-old alternative formulation of electrodynamics. The documents had been written, they had been peer-reviewed by the standards of their day, they had been used as the standard formulation across a continent for 2 generations, and then the discipline had let them slip into a language most physicists could not read, and the discipline had stopped reading them. Assis has put them back into the language the discipline now works in. The discipline is mostly still not reading them. This is the kind of work that, in another field, would have produced a school. There would be graduate students writing dissertations comparing the Assis translated Ampere to the standard textbook treatment. There would be conferences on the foundational implications of the Weber force law in the modern era. There would be young theorists trying to derive the Maxwell-Lorentz framework from the Ampere-Weber framework as a coarse-grained approximation, the way Newton's gravity was eventually shown to be the long-distance limit of general relativity. None of this is happening. The translations sit on the shelves of the physicists who are interested in them, and they are not moving from those shelves to the curriculum. 2 faces of one law. Earlier in this video I asked you to remember that phrase. We are returning to it now, but the meaning has shifted. The law has 2 faces, the sideways magnetic attraction and the head-to-tail longitudinal repulsion. And for 2 centuries, only one of those faces has been carried forward into the language the discipline is currently working in. The other face was written down by Ampere in French. It was generalized by Weber in German. It was used across the continent for 2 generations. It was filtered out of the textbooks in the late 19th century. And it has now finally been translated into English by a single Brazilian physicist working in São Paulo, who has spent 30 years of his career restoring access to a document that the discipline had quietly let go of. The door is open. The translation exists. The original argument is now in the language the discipline reads. Nobody, in numbers, has walked through the door. Part 10. The Web that Holds the Universe. Up to this point in the video we have been at the scale of a benchtop. A wire, a battery, a coil of copper, a fragmenting strip of foil, a graduate student with a clipboard in a room with fluorescent lights, and a capacitor bank. The whole question has lived inside instruments you could hold in your hand, or at least move with a hand truck. I am about to take you somewhere else. The longitudinal force question, if it matters at all, does not only matter at the bench, it matters most, if it matters at all, at the scale of everything that exists. So look up. If you walk outside on a moonless night, far enough from any city that the sky is dark, and you let your eyes adjust for half an hour, you will see, if the season is right, a faint band of haze running across the sky. That band is the Milky Way. You're looking edge-on at the disk of the galaxy you live inside. There are roughly 400 billion stars in that disk. Each of those stars is, like the Sun, a plasma, a collection of charged particles, hot enough that the electrons have been stripped from their atomic nuclei and are flowing around freely. The space between the stars is also plasma, much thinner, much colder, threaded with magnetic fields whose origin nobody has entirely explained. Now zoom out. The Milky Way is one galaxy among about 2 trillion in the observable universe. The galaxies are not distributed uniformly through space. They are clustered. They are clustered into groups. The groups are clustered into superclusters. The The superclusters are arranged along filaments, and the filaments are arranged into a vast cosmic-scale structure that astronomers, for the last 40 years, have been calling the cosmic web. The web is the largest structure in the universe. It is the framework on which everything else hangs. The geometry of the web is striking. The filaments are thin, by cosmic standards, and long. A typical filament segment might be 20 or 30 million light-years across in cross-section, and stretch for hundreds of millions of light-years along its length. Between the filaments are vast empty regions called voids, hundreds of millions of light-years across, containing almost no galaxies, almost no gas, almost nothing. The matter in the universe is not spread out evenly. It is concentrated into thin, lacy strands separated by mostly empty space. The strands are where the galaxies live. For most of the last 40 years, the cosmic web has been studied indirectly. You can infer the structure from the distribution of the galaxies you can see. You can map it using gravitational lensing, the way the gravity of foreground matter bends the light of background quasars and galaxies. You can simulate it on enormous computers using the standard cosmological model with its dark matter scaffolding, and the simulations produce structures that look a great deal like what the surveys see. The web is real. The web is mapped. The web is one of the most studied objects in modern cosmology. What was missing, until very recently, was direct images of the filaments themselves. The filaments are made mostly of diffuse hydrogen gas, and diffuse hydrogen at intergalactic densities is extremely difficult to see. It does not glow brightly. It does not emit in the wavelengths that ordinary telescopes are tuned for. It is there, in immense quantities, but it is faint, and to image it directly you need a very specialized instrument and very long exposures. In 2020, that direct imaging finally happened. A team using the Muse spectrograph on the Very Large Telescope in Chile pointed the instrument at a patch of sky carefully chosen for its emptiness, a patch that, by ordinary criteria, contained almost no visible galaxies, and they integrated for hundreds of hours. What they got back was an image of the cosmic web, not the inferred web, not the simulated web, but the actual web, the faint glow of intergalactic hydrogen threading across the patch of sky in long, thin filaments, with galaxies strung along the filaments like beads on a wire. The image was published. The web, for the first time in human history, had been seen directly. I want to take you to the moment of that observation. Look up at the cosmic web through a telescope that does not exist on your roof, but does exist on a mountain in Chile. The Muse spectrograph on the Very Large Telescope. You're looking at a patch of sky that contains nothing visible to the naked eye. The instrument integrates for hundreds of hours and resolves. Faintly, the glow of hydrogen filaments threading through that patch of sky. Each filament is 20 or 30 million light-years across. Galaxies are strung along the filaments like beads on a wire. The voids between contain almost nothing. The filaments are threaded with magnetic fields whose origin nobody has explained. You're looking at the largest known structure in the universe, and the question of whether the currents in those filaments talk to each other directly is the question Ampère asked at a workbench in Paris 200 years ago. The patch of sky is small. The structure is enormous. The light you're catching has been travelling toward you for billions of years. Here is where the longitudinal force question re-enters the story, because the cosmic web is not just a structure. It is a network of plasma filaments. Plasma is, by definition, made of moving charges. Wherever there are moving charges in any meaningful quantity, there are currents. Currents in plasma filaments. Currents at the scale of the universe. The currents in cosmic plasma are not hypothetical. They have been observed at every scale at which observations are possible. The smallest scale is Earth's own magnetosphere. The Norwegian physicist Christian Birkeland, working from a polar observatory in the early 1900s, proposed that the aurora was produced by electric currents flowing along magnetic field lines from the Sun into the polar regions of Earth. He proposed the current in 1908. The currents were directly measured in 1974 by NASA's Triad satellite passing through the polar magnetosphere. They are real. They flow continuously. They are called Birkeland currents, after the man who proposed them, and they have since been measured by every magnetospheric satellite that has gone up: MagSat, AMPTE, Cluster, Themis, MMS, and others. The currents are not unique to Earth. The Galileo spacecraft observed Birkeland currents in Jupiter's magnetosphere in the 1990s. The Cassini spacecraft observed them in Saturn's magnetosphere in the 2000s. The Juno spacecraft has been observing them at Jupiter again since 2016. Anywhere there is a magnetized plasma in a planetary magnetosphere, there are Birkeland currents flowing along the field lines. The currents are not unique to planets. They have been observed in the solar wind. They have been observed in the interstellar medium, in the helical filaments around the Cygnus X region, and in the Eridanus loop. They have been observed, through their synchrotron radiation signatures, in the spiral filaments around galactic jets. At every scale where the instruments are good enough to look, the universe has currents. The currents thread the magnetic fields. The magnetic fields thread the plasma. The plasma is most of the visible universe. I want to dwell for a moment on the strangeness of how much current is actually flowing in the universe, because the strangeness is hard to feel from the textbook descriptions. The Birkeland currents flowing through Earth's polar magnetosphere, in ordinary quiet conditions, carry on the order of 1 million amperes of current at any given moment. During a major geomagnetic storm, when the sun has thrown a coronal mass ejection at us and the magnetosphere is responding, the current can climb to 10 million amperes or more. These are not abstract numbers. These are real currents, flowing in real charged particles, in real time, in the magnetic field-aligned channels above your head. The same scale of current, or larger, has been measured in Jupiter's magnetosphere, in Saturn's, in the solar wind, in the interstellar medium wherever the instruments are good enough to look. The currents flow continuously. They have been flowing for as long as there has been a sun and a magnetized Earth. They are not exceptional events. They are the background condition of the cosmos. When you scale this up to the cosmic web, the numbers become harder to compute, because the column densities of the intergalactic plasma are not as well measured as the planetary magnetospheres. But the order of magnitude estimates that have been done, by Pratt at Los Alamos, by other researchers in the plasma cosmology tradition, suggest that the currents flowing in cosmic web filaments integrated over the cross-section of a filament tens of millions of light-years across could be on the order of 10 to the 18 amperes per filament. 10 to the 18. A billion amperes. The numbers are enormous, even allowing for substantial uncertainty in the column densities. The currents are there. They thread the cosmic web at scales that, if you stop to think about them, become hard to hold in mind. The role of these currents in the large-scale structure of the cosmos, whether they shape the structure or merely decorate it, is one of the open questions of modern astrophysics. The mainstream model, the one in every textbook and every introductory course on cosmology, says that the structure of the cosmic web is gravitational. Dark matter forms the scaffolding. Ordinary matter falls into the gravitational wells produced by the dark matter. The resulting filamentary geometry reflects the initial density fluctuations of the early universe, expanded and elaborated by gravitational collapse over billions of years. The plasma currents that thread the filaments are, on this view, a consequence of the structure, not a cause of it. There is a minority view, held by plasma physicists in the tradition of Hannes Alfvén, the Swedish physicist who won the Nobel Prize in 1970 for his foundational work on magnetohydrodynamics, which is the standard theory of how plasmas behave in the presence of magnetic fields. Alfvén argued, in the decades before his death in 1995, that the discipline of cosmology had underestimated the role of electromagnetic forces in shaping cosmic structure. He thought the cosmic web in particular was at least partly shaped by Birkeland currents at scale, and that the standard purely gravitational model was leaving important physics on the table. His student Anthony Peratt at Los Alamos National Laboratory has continued the program, publishing simulations and analyses for decades arguing that plasma current effects at cosmic scales can produce structures resembling the observed cosmic web. The work is published. It is not mainstream. It sits, like Grano's work, in a quiet corner of the literature, respected by a small community, not taken up by the broader discipline. If Ampere's longitudinal force is real, and if Birkeland currents at the scale of the cosmic web are dynamically significant, then the cosmic web is doing something that ordinary magnetohydrodynamics does not capture. The longitudinal force would couple distant parts of the filaments to each other in a way that the perpendicular magnetic forces would not. The coupling would fall off with distance. Ampere's law goes as 1 over r squared, the same as Newton's gravity and Coulomb's law, but it would never quite vanish. The total effect across a filament tens of millions of light-years long, integrated over the immense column density of plasma, could in principle be a significant contributor to the filament's evolution. This is not a fringe claim. This is the obvious thing to check if Ampere was right at the benchtop. The discipline has not, on the whole, checked it. The mainstream framework assumes the longitudinal force is not there, and so the mainstream simulations of cosmic web evolution do not include it, and the absence of any obvious anomaly in the simulations is taken as evidence that the longitudinal force is not needed. The minority framework includes the longitudinal force, and the minority simulations show that it might be doing real work, and the disagreement between the two simulations is not the kind of disagreement that the discipline currently has the institutional capacity to resolve. We have looked at a benchtop in Paris in 1820. We have looked at a benchtop at MIT in 1989. We are now looking at a structure tens of millions of light-years across, threading the universe, possibly carrying currents whose interactions, if Ampere was right, would couple distant galaxies in ways the standard story does not allow for. The benchtop question has just become a question about the structure of everything that exists. Part 11. If the cosmic web speaks. I want to lay out the possibility honestly, because the possibility is the thing the rest of this video has been building toward, and I do not want to overstate it, and I do not want to understate it. If Ampere was right at the benchtop, if the longitudinal force is real, if the exploding wire experiments and the aluminum foil fountain experiments are showing us a force that the standard framework does not include, then the question of whether the same force matters at cosmic scales is not a question of whether new physics is needed. It is a question of whether old physics, derived 200 years ago and quietly removed from the textbooks a century ago, is being applied to the cosmic web in the way that, if it is real, it would have to be applied. This is not the same as saying that gravity is wrong. The cosmic web is, by every reasonable measurement, primarily gravitationally organized. The dark matter scaffolding is real. The infall of ordinary matter into gravitational potential wells is real. The filamentary geometry that emerges from gravitational simulations of the early universe matches, in broad strokes, what the surveys observe. To say the longitudinal force might matter at cosmic scales is not to say gravity does not matter at cosmic scales. It is to say that, in addition to gravity, there might be a slower, weaker, but never vanishing coupling between distant parts of the web, mediated by direct charge-on-charge interaction in the Ampere sense, that the standard simulations do not include. If that coupling is there, what would it do? It would first couple the dynamics of distant parts of the web in a way that the local gravitational simulations cannot reproduce. A region of the web in one part of the universe would, through the longitudinal force, exert a small but non-vanishing influence on a region of the web in another part of the universe. The influence would fall off with distance, but slowly enough that integrated over the full extent of a filament, it would not be negligible. The web, in this picture, would not be a collection of independent local structures held together by their own gravity. It would be a single connected system, with each part in immediate or near-immediate interaction with every other part. This is structurally a Machian picture of the universe. Ernst Mach, in 1883, in his great work on the history and foundations of mechanics, proposed that inertia, the resistance of an object to changes in its state of motion, is not a property of the object in isolation, but a relationship between the object and the rest of the matter in the universe. The classic example is a spinning bucket of water. The water, in the spinning bucket, knows to climb up the walls and form a concave surface. Newton's account of this is that the spinning is happening relative to absolute space, an absolute structure independent of any matter, and the water is responding to its motion through this absolute structure. Mass said this was metaphysics dressed as physics. The water knows it is spinning, Mach said, because the rest of the matter in the universe is not on average spinning with it. The reference frame is not absolute space. The reference frame is the rest of the universe's matter. Inertia is a relationship, not a property. Einstein admired Mach's principle. He tried to build general relativity in such a way that Mach's principle would emerge naturally from the equations. He was not, in the end, fully successful. General relativity has solutions in which an object in an otherwise empty universe still has inertia, which is hard to reconcile with strict Mach. The principle survives as an inspirational idea, a guiding intuition, more than as a strict consequence of the modern theory of gravity. Direct action electrodynamics offers a route to a Machian universe that gravity does not quite offer. If every electric charge is in immediate or near-immediate interaction with every other electric charge in the universe, through the longitudinal force, through whatever direct action mechanism Ampere's law really describes, then the local behavior of any particular charge depends, in a real and quantifiable way, on the configuration of all the other charges. This is not strict Mach in the inertial sense, because the interaction is electromagnetic rather than mechanical. But it has the same structural property of universal interconnection. Every charge is, in a sense, listening to every other charge. The cosmic web in this picture is not just structure, it is conversation. I have been saving the weight of this for the right moment. Sit with it now. The possibility, held by some physicists, dismissed by most, never quite settled by the evidence either way, that what we are looking at when we look at the cosmic web is not just structure, that it is also communication, every moving charge in every galaxy nudging every other moving charge, slowly and faintly, across distances that no other signal can cross. A universe in which the matter is, in a sense that we have spent 2 centuries refusing to take seriously, in touch with itself. The weight of this is the listener realizing, possibly for the first time, that this is the kind of question a physics discipline can decide to stop asking, and then to discover, 2 centuries later, that the question was never actually closed. There is another resonance I want to mention before we move toward the close, because it has been hovering in the background of this discussion since the first time we mentioned direct action at a distance. In 1945, 2 American physicists named John Wheeler and Richard Feynman, Wheeler the older, Feynman the much younger, just out of his Princeton graduate student years and not yet famous for any of the things he would later be famous for, published a paper called Interaction with the Absorber as the Mechanism of Radiation. The paper proposed a complete reformulation of classical electrodynamics in which the fields themselves were not fundamental. The fundamental thing, in Wheeler-Feynman theory, was the direct interaction between charges. The fields were a convenient way of summarizing those interactions, but the fields had no independent ontological status. Wheeler-Feynman theory is not Ampere's theory. It uses different mathematics. It makes different specific predictions. It rests on a particular ansatz about time-symmetric exchange of advanced and retarded waves that has not, in the end, been entirely successful as a foundation for quantum electrodynamics. Wheeler himself, in his later writings, expressed regret that the theory had not, quite, worked out. But the family resemblance to direct action electrodynamics is real. Both treat the fields as derived. Both implicitly require the rest of the universe to participate in any local electromagnetic interaction. Both restore, in their respective ways, the Machian structure that Newton's framework had removed. There is, in the absorber theory picture, a peculiar feature that is worth dwelling on for a moment, because it is the feature that, if anything in the late Grano and the Wheeler-Feynman family resemblance is pointing at something real, would constitute the structural payoff of the whole reformulation. The peculiar feature is this. In a direct action electrodynamics, the interaction between a local charge and the rest of the universe is, in some literal sense, present at every moment. The local charge does not have to wait for a signal to arrive from a distant charge, because there is no signal travelling through an intervening field. The two charges are in direct contact, mediated by the structure of the law itself rather than by anything propagating through space between them. The far end of the universe is, in this picture, not far away. It is, in the only way that matters for the interaction, present here, now, contributing its small influence to whatever the local charge is doing. The implications, if you take this seriously, are larger than I want to attempt to spell out in a single video. They touch on questions about the nature of time, the nature of causality, the meaning of locality itself. The Wheeler-Feynman papers take the implications seriously, but cannot in their original form resolve them. The discipline, for the most part, has not taken the implications seriously, and has not had to resolve them. The picture sits, waiting, in the foundational literature. It is the kind of picture that would, if it were the correct picture, require a substantial rethinking of how we describe the universe at its larger scales. The Wheeler-Feynman framework is not mainstream. It is taught in some advanced electrodynamics courses as a curiosity. It is referenced occasionally in foundational discussions of quantum mechanics. It sits alongside the Ampere-Weber framework as a 20th century example that direct action electrodynamics is at least logically coherent under modern conditions. The two of them together, Ampere and Weber in the 19th century, Wheeler and Feynman in the 20th, form a kind of secondary tradition in the history of electrodynamics, a tradition that the mainstream has set aside but that the mainstream has not refuted. The pieces, taken together, fit. The benchtop experiments in the 80s showing fragmentation and excess kinetic energy. The cosmic web filaments imaged in 2020 showing structure that the gravitational model handles in broad strokes, but that has detail that the plasma current model handles better. The Birkeland current observations at every scale, showing that currents really are ubiquitous in the cosmos. The Mach intuition that inertia is a universal relationship rather than a local property. The Wheeler-Feynman demonstration that field-free direct action electrodynamics is logically coherent. The Assis translation putting the original Ampere memoir back into the language the discipline reads. The pieces are on the table. They have been on the table for decades. Nobody has put them together with the institutional weight that putting them together would require, and so they sit on the table separately, looking very much like a picture nobody has assembled. A weight settles. The question of what the universe is made of has not been answered. It has been postponed for 200 years. Part 12. Two Faces of One Law. We're at the end of the video. I want to take you back one more time to where we started. It is the spring of 1820 in Copenhagen, and a compass needle has just moved. The needle moved in a direction nobody had been looking for, because nobody had thought that a current-carrying wire and a magnetic compass had anything to do with each other. The needle moved because the law connecting them was not the law anyone had been guessing at. It was a law sideways from the obvious guess. It is the autumn of 1820 in Paris, and a 45-year-old French mathematician is walking home from a meeting at the Institut de France, and he has just realised that the rest of his life is going to be spent on the law that needle moved by. He goes home. He does not sleep. He spends 7 days building the apparatus, and on the 8th day he stands in front of his colleagues and demonstrates parallel currents attracting and anti-parallel currents repelling, and coils behaving like magnets. He goes back to his apartment, and he spends the next 6 years at a knife-edge balance, measuring the force between two short segments of current at every angle he can construct. He writes down both the sideways magnetic attraction and the head-to-tail longitudinal repulsion, because the law that produces them is one law, and the law is the law. The geometry of the world is the geometry of the world. In 1826 he publishes the memoir, and it is received as the founding document of a new science. the 7 days. I asked you, earlier in the video, to remember the 7 days. We are back to them now. The 7 days are a measure of how fast a discipline can move when a single mind has caught fire. From the 4th of September to the 11th of September, in 1820, one person rewrote the foundational sentences of a new physics. 7 days. The pattern of the law, the first solenoid, the first galvanometer, the first quantitative hypothesis about the force between current segments, all of it in 7 days by one person, alone in an apartment in Paris. Hold the 7 days in mind. Now hold the 200 years that followed. 200 years in which the discipline that began with those 7 days has spent its time displacing, slowly, the formulation that emerged from them, replacing it with a more compact formulation that did not include the longitudinal half, training generations of physicists who never encountered the original, allowing the original to drift into a language most working physicists could not read, then translating it back, then declining to read the translation. 200 years of declining to settle the question that Ampère, in his 7 days, opened. The contrast is hard to look at. A mind can rewrite a science in a week. A discipline can decline to settle the question that mind opened for 2 centuries. The asymmetry is, in a way, the asymmetry between people and institutions. People can move fast when the problem is in front of them. Institutions cannot. Institutions move at the pace of curricula and committees and the slow filtering of ideas through textbooks. When a question is large enough to require an institutional answer, and not just a personal one, the answer can be postponed indefinitely. Ampère gave the discipline the question. The discipline has not, in 2 centuries, given the answer. 2 faces of one law. We started this video with that phrase. We are ending with it. The law has 2 faces. One face is the sideways attraction between parallel current segments. That face survived. It is in every textbook. It runs every electric motor, every transformer, every speaker, every MRI machine, every chip in every device you have ever owned. It is the face the discipline kept, and the face it built the modern world on. The other face is the head-to-tail repulsion between collinear current segments. That face did not survive in the textbooks. It survived in Ampère's memoir, in Weber's 7 memoirs, in the original French and the original German, on the shelves of physicists who could read those languages. It survived in the wire fragmentation patterns at the Naval Surface Warfare Center in 1964. It survived in Peter Granot's exploding wire papers across the 1980s. It survived in the aluminum foil fountain experiments at MIT. It survived in the Assis translation of 2015, which finally put the original memoir into the language the discipline currently reads. It survived. It didn't flourish, but it survived. The face that survived in the textbooks runs the modern world. The face that survived only in the literature, only in the experiments, only in the translations. That face is the one that might, if it is real, be holding the universe together. Each Birkeland current threading the cosmic web. Each plasma filament tens of millions of light-years across. Each region of the visible universe in slow direct action contact with every other region, through a force that the textbooks dropped, because it integrates to 0 in closed circuits, but does not, plausibly, integrate to 0 across the structure of the cosmos itself. 2 faces, one law. The face we kept built the modern world. The face we dropped might be the one that built everything. There is a wire in the wall of the room you're listening in. Right now, current is flowing through it. If Ampère was right, and the discipline that grew out of his work has not, 2 centuries later, decisively settled whether he was right or not, then the moving electrons in that wire are pushing on each other along the wire's length, head to tail, in addition to the sideways forces that the textbook framework tells us are there. The wall feels the longitudinal push. The wall does not move because the wall is much stronger than the push. The push is real anyway in this picture. It is small. It is not 0. It is happening right now, in every wire, in every room, in every building in the world. And if Ampère was right, the same thing is happening, at incomparably larger scale, in every Birkeland current threading every plasma filament in the cosmic web above the roof of the building you're listening in. Every moving charge in every galaxy is nudging every other moving charge, slowly and faintly, through the longitudinal force, across distances no other signal can cross. The Milky Way is in touch with Andromeda, in this picture, not just through gravity, but through direct charge-on-charge interaction along the currents that thread the intergalactic plasma. The cosmic web is not just structure, it is possibly conversation. The universe is, possibly, in touch with itself in a way the standard story has spent 2 centuries refusing to take seriously. Ampère insisted we measure it. He spent 6 years measuring it. He wrote the law down with both faces. He published the memoir. He died in 1836 with the inscription Tandem Felix on his tomb, at last happy. He thought he had finished it. Maxwell insisted we respect it. He devoted an entire chapter of his treatise to it. He called it one of the most brilliant achievements in science. He noted that it satisfied Newton's third law in its strongest form, and then he replaced it, gently and explicitly, with a formulation that did not include the longitudinal face. And we, the discipline that inherited both of them, the discipline that built the modern world on the face of the law that Maxwell's framework kept, the discipline that quietly let the other face drift out of the textbooks across 2 generations. We have not, 2 centuries later, decided whether the face we dropped was a mistake we should correct or a complication we were right to leave behind. The question is open. It is still open. It has been open since 1826, and it is open tonight. The wires in your walls, the cosmic web above your roof, the face of the law the discipline kept, and the face the discipline let go. 2 faces of one law. One face we built our civilization on. The other face we have spent 200 years declining to settle. Maybe the discipline will eventually return to the question. Maybe a generation of physicists trained outside the assumption that the question is already closed will look at the Grano papers and the Académie translation and the cosmic web observations and decide finally to put the pieces together. Maybe the answer will turn out to be that Maxwell Lorentz really was the whole story, and the longitudinal face really was just a mathematical artifact of an old formulation, and the universe is held together exactly the way the textbooks say it is. That is possible. The mainstream view may be right, but it has not, 2 centuries on, been demonstrated to be right. It has been assumed. The assumption has been worth questioning for 200 years. The question has been on the table for 200 years. The answer has been postponed for 200 years. The wires in your walls carry current. The cosmic web threads the universe. The needle moved in Copenhagen. Ampère built the law in 7 days. The discipline forgot half of it across 2 generations. And the question of whether the half we forgot was, all along, the half that holds the universe together is still, on this night, on every night, unanswered. We have spent 2 centuries declining to find out. Maybe the next generation will not. Maybe the next generation will look up at the cosmic web on a dark night and remember that there was a man at a workbench in Paris 2 centuries ago who measured both faces of the law that ran through it and decided that both faces were the law because the geometry of the world is the geometry of the world, and you do not get to keep the parts of it you like and throw away the parts you find inconvenient. Maybe that generation will read the Académie translation. Maybe they will reproduce the Grano experiments in better laboratories with better instrumentation than the Francis Bitter Lab had in 1989. Maybe they will run the cosmic web simulations with the longitudinal force included and see whether the simulations match the observations better than the gravity-only simulations do, or worse. Maybe they will, in their own 7 days or 7 years, settle a question that has been sitting on the table since 1826. The 2 faces are still there. One face built the modern world. The other face is, maybe, the one that built everything. The discipline has not decided. The wires in your walls do not know the discipline has not decided. The cosmic web does not know the discipline has not decided. They are doing what they do. They were doing what they do before Ørsted's compass moved in Copenhagen, before Ampere walked home from the Institute, before Maxwell wrote the treatise, before Lorentz wrote down F equals QE plus V cross B, before Grenot watched the aluminum foil leap and the water column climb to the ceiling, before Assis translated the memoir into the language the discipline reads. They were doing it then. They are doing it now. They will be doing it long after every textbook now in print has been replaced. The geometry of the world is the geometry of the world, two faces of one law. We have not, in 200 years, settled which face was the whole truth. The question is still open. It is still open tonight.